Hello guys, welcome back to Tax Riders and another episode of Finite Element modeling series. In this video, we're going to solve the heat transfer inside this helical shape, this time in OpenFOAM. Although OpenFOAM is usually used for fluid dynamics, but we want to use it for heat transfer problems. Let's see how we can do that. Okay, in the previous video I showed you how to install OpenFOAM. That video actually belonged to the Set Up Your Environment series. But you saw how easy it is to install OpenFOAM. And then now we want to use OpenFOAM to simulate heat transfer. OpenFOAM is a very powerful fluid dynamics solver. It is usually used for computational fluid dynamics, CFD studies. But in this video, we want to use it for the study of heat transfer inside our complex shape. And this will be very exciting because we need to convert the mesh to a format that OpenFOAM can understand. We will use OpenFOAM mesh conversion tools. OpenFOAM is released with a lot of converter tools, I will say. And we will take advantage of one of the examples in OpenFOAM, which, as I said before, will act as a template for us. And for solving this kind of heat transfer, mass transfer stuff, there are a couple of different solvers in OpenFOAM. But because we want to use a transient, we want to actually simulate a transient behavior, we will use Laplacian foam for this. So the first step is preparing the mesh. In order to prepare the mesh, I will load the geometry that we prepared in the second episode, again in SALOME. And I export the mesh in a format that is very easy to convert to something that OpenFOAM can understand, which is actually the UNV format. Let's run SALOME and open our mesh, our HDF file, which is something that we produced in a second episode, which is actually this helical shape. Because I have actually downgraded my SALOME version. Now I think I need to regenerate the mesh, but as you can see that it's very nice that SALOME has a kind of backward compatibility, that I can open the files that are generated, that are created in newer versions in older versions. So this is the spring, and you know that now we have the inlet here, outlet here, and the wall here. Cool. So we go to the mesh module. We did what we did in the Elmer video. In the video that we solved this problem using Elmer, you saw that I rescaled this geometry into something smaller because this is actually a very big geometry. But since OpenFOAM has quite stable solvers, that's very easy to deal with these geometries, even in this size. What we need to do is actually defining a big, let's say, coefficient for diffusion. That's what we need to do. And then you will see that OpenFOAM is very handy, is very powerful in solving these kind of problems. So let's go to the mesh module, and here I think, yeah, you can see that it doesn't let me open the mesh because this is generated in newer versions. So I need to recompute the mesh. It's fine, on your system. You don't need to do that. This is just because, as I said, I downgraded the version of SALOME. And then when the mesh is ready, I have defined the mesh parameters in the second video of this series. So now I will have the mesh that is really appropriate for performing finite element analysis and finite volume analysis. Let's let it produce the mesh for me. And now it is done. I can close this evaluation window. This is the mesh that we've been using in other episodes, and this is a finite element mesh, but also finite volume is also capable of handling irregular shapes, irregular elements, let's say, and that's why we can use this mesh in a finite volume solver like OpenFOAM as well. And let me double check if the groups are created here. This is the wall, this is the inlet, this is the wall, and this is the outlet. So these are the names that we need actually when we convert the mesh to something that OpenFOAM can import. So I export it, as I said, to UMV file. Previously we used this GMF file to convert it to something that FreeFrame can understand, and then we also use, I think, UMV for in the Phoenix video that we wanted to convert it to Gmesh format. But now I use this UMV file again. So I save it on the desktop as helix. It can be helix.umv. So I save it. And then here I have the UMV file. So now I can save the study, and I open a terminal. And this is actually now I want to check for the name of the converter. As you can see, there are lots of converters. For example, ANSYS to foam or Gmesh to foam. Lots of converters, and the converter that I want to use is IDS UNV to foam, because as you saw here, that's the name of this format, that is IDS UMV. So now I can use this converter to convert this UMV file to a format that OpenFOAM understands. But before using that, I need to prepare a structure, or let's say the structure that OpenFOAM projects have. Most of the projects are actually structured in that way, and this is actually the structure that OpenFOAM requires to understand the physics of the problem. We need to first prepare that structure, and then we put this helix UMV there and call this converter at that structure directory, because then it puts the output at the location that OpenFOAM expects. So this is a better idea. Let me do that instead of converting it here. So as I said, we need to copy one of the examples in the OpenFOAM tutorial, as I showed you in the previous video, in the installation video, and then that can be the starting point for us, that we don't need to start from scratch. Let me go to the OpenFOAM tutorial directory. So as I showed you, it is OpenFOAM tutorials, and then I told you that here you can find for example, let's say I would see name equals Laplacian, because I don't know where the Laplacian foam examples are located. I can search for Laplacian foam, and you will see that it's actually a kind of solver. You can see this is again in openfoam.com, but you can, as I described in the previous video, this is a kind of discussion, kind of decision that you need to make before using OpenFOAM. In this case, I've used openfoam.org version, but I can always refer to the documentation of the other version. So it says that the solver is the Laplacian foam is a kind of solver that can solve this equation for us. And you're absolutely right. This is the equation that we want to solve. We solved previously in Phoenix, in Elmer, and in FreeFrame, and now we want to solve it using OpenFOAM. And it says that what is really important to change is the diffusion coefficient, because this is actually the only parameter that this model has, more or less, let's say. And here it says that that the examples or the tutorials or examples are located here in basic Laplacian foam. But if I didn't want to refer to the documentation, this was the way to check where the examples are located. So you can see that I use the find command in Linux and -name Laplacian asterisk, and now it shows me that it is actually inside the basic directory. So basic directory, there are lots of solvers here, you can see the potential and scalar transport, and then inside Laplacian, this is where the file, the tutorials are located. In this case, it is only one example, which is, I think, something with ANSYS. Yeah, this is an ANSYS file that you need to convert back to OpenFOAM, and then you can call these files to run the example. So, for now, I copied this path. So I go back to desktop, to the desktop directory, and I copy recursively here OpenFOAM, Laplacian OpenFOAM, and then flange, yeah, I should have copied flange as well, to here, to current directory, which is now the desktop directory. So I came here on the terminal, and now I press enter, so we can see that this is copied here. And I can change the name. I can use the terminal to change the name. It doesn't matter. I can say like transient heat, which is actually the problem that we are going to solve. So I go inside it, transient heat, and now you will see that we have the structure like this. I don't want to use these files because I want to just show you how we can run the things ourselves, and I remove this file because this is not the input file that I want to use. And now it's the time that we put the helix unv file here, and we call the converter on this file, and it converts the file, the mesh, to something that OpenFOAM expects, which is putting the file in a new format inside this constant directory. You can see that it's now empty. It contains only the material property file, which I describe later how to use it. But after we convert this, it puts the file there. So it was, as I told you, IDS unv to foam, and then helix.unv. So we press enter, and you can see that now it says that there are three groups as it was here. Actually, inlet, outlet, and wall. And then you can see that these are the things, and these are the number of nodes, actually, which are called patches here, that the surface contains. So here, and then, and also the wall. And these are the things, the labels that we need to use. But before before modifying the template to something that we want, let's check if everything is correct. And you can see that the mesh is now converted to a directory called polyMesh, which contains the boundaries, the faces, and the points, everything. But these things are actually created using this converter. So you can see that how easy it is to convert any shape that you have inside any program, any CAD or CAM engineering application, like in this case SALOME, to something to OpenFOAM input. And this is actually the way. But let's go on and modify the whole example. Let me open this in a structure that is easy to navigate. So I open all the directory structure in Atom as a project to show you how the relative structure. So this is the whole structure, the project tree, let's say, and this is the polyMesh directory I showed you. This is the zero. This is actually the naming convention, the way that OpenFOAM stores files. So 0 means initial state, if it is a transient solver, or all the properties that you want to assign to the material for the initial state or initial condition. And then here we have control dict, scheme, and solution. These files are very important, and the most important one is actually control dict, which we need to modify to reflect. For example, here you see that the start time is this one, end time is 3. Usually we had the simulations up to 20 at the time step, and delta t, this is yeah, we can we can change it, or yeah, this is a very small time step, probably because we want to use a very big diffusion coefficient. It's not really necessary to have such a small time step, but let's leave it for now. And writing interval is the interval that we want to write the files. I will change it to half because we have 20 steps, and it is actually each 100 steps. That's why I said this is very small, but I want to write it every like half a time scale. If it is seconds, this is half a second. If it is a day, half a day. But in this case, OpenFOAM, I will show you, the unit that it has is actually per second, so it is 20 seconds, and this is writing the output every half a second. So there are also write precision, time format, all these things are controlled here, and this is you can always say start from the latest time. This is the latest time is 0 in this case, but if you interrupt the simulation at any time point, or you continue till the last time point and you want to continue the next simulation from the end of the previous simulation, this is the way that is implies that always start from the latest time point. So I saved this file, and these are more advanced things for the solvers. Actually, for the numerical scheme, finite volume method scheme that OpenFOAM will use. In this case, it's more precise to say Laplacian foam uses to solve the equation that I showed you here. This is the equation that we are going to solve. And then the solution is similar to that for, the kind of, more settings for the solvers, and the way that it can treat different variables. In this case, there's only one dependent variable, t, and we want to solve it for that. But another thing that is very important here is the transport equation, transport properties, which is the material properties, in this case, this dt, diffusion coefficient. This is a very small number regarding the big size of the domain that we have. So I change it to like this, which is a very big 10,000. A very big one in this scale, meter per second. This is a way that, lots of engineering programs you'll see that describe the units. So each number has, is the degrees of any basic units. And here is the length, this is time. And when you say 2, it is meter squared per second. It means -1, it's to the -1, so it's sort of dividing by that. So a squared meter divided by time, in this case second. So this is the units and this is the value. And then this is the other one that is actually, it says that it is a 3-dimensional case, and the internal field initially it has like 0 for the temperature, 273 Kelvin. And then here is where we need to change these things to the labels that we had. So if it is 0 gradient, it's better to say that the wall was the 0 gradient. Patch 2, these are for the flange example. I don't need these things. I change them to the one that I want. So input, we had always plus 20, so 293. For the input, and then for the output minus 20, which was 253. And you can see after converting the mesh to the OpenFOAM format and taking advantage of the examples as a template, how easy it can be to set up an OpenFOAM simulation. So yeah, we are done. Actually, we are done. We have set up everything we wanted, transport properties, and this is not required anymore to be here because it's already converted to the OpenFOAM format, and that's it. And we are ready to run Laplacian foam. So I can say that Laplacian foam. To run it here, this is something that we need to evaluate if this time step is good or not. I think this is very low, but let's run it first and we will see what happens. So I press enter, no argument. We are inside this structure, in the root of this structure, and we press enter. And now you see that it starts to solve it. It's quite fast. I told you OpenFOAM is amazing. It solves things very fast. So you see that even though it required 100 steps for each write, for each result step to be written on the disk, you can see that how fast it works. And this is actually still a sequential simulation. I haven't used any parallel features of OpenFOAM. And when it is done, we can use the ParaView software to visualize the results. We can use, as I described in the previous video, we can use ParaFOAM, that is a version of ParaView installed with OpenFOAM, or you can use the version that you have on your system. This is completely up to you. So now it is over. And now I can run ParaView on my system to visualize the results. So I run ParaView. And as I told you in the previous video, we should navigate to the structure. And then we open the control dict file inside the system directory. We switch to all files. We open control dict. It asks us for the reader because it cannot detect the format, and we need to select OpenFOAM reader for that. So I open it and press apply, and wow, this is our helical shape. As you can see, we have T here in two different formats, both element-wise and node-wise. So I open the node-wise one, and as you can see, this is the first time step. But you know that the reason that it has a fast diffusion is because we chose a very big diffusion coefficient. And I press run, and wow, you see that how nice it actually starts to the different fronts, the temperature fronts or heat fronts, they start to approach each other. So this is quite nice. The way that we took advantage of OpenFOAM. As I told you, OpenFOAM is quite powerful solver especially for fluid flow problem, but in this case we use it for the heat diffusion simulation. And yeah, so that was the directory structure, and these are the files. And as you saw, it's quite simple to use this powerful open source solver to solve the problem that we had in a relatively complex shape. Yeah, I hope you find this video useful, and see you in next videos. Bye.